Hysteresis can be described as the lagging of an effect after an event. Might be difficult to get your head around that immediately, but let me try and explain that in this particular case. And we are talking about magnetic hysteresis, because hysteresis occurs throughout the world in different forms. So here I have a piece of unmagnetized metal. Let's say it's iron for the sake of argument, so it has no magnetism whatsoever. And we've wrapped a coil around it, and we're going to pass a current into that coil. Passing the current into the coil will make it into a magnet, and that is the event that we're going to start our process with. So let's have a look at it. We're going to pass a current in there. So current going in there. This will give this magnet a particular polarity. The current will flow and make an electromagnet. So let's try and describe on these axes, what is happening. On this vertical axis up here, I'm going to talk about the flux density. So flux density is V. And on this horizontal axis along here, I'm going to talk about the current. Technically, that's not the term I need to be using there, but I'll come back to this towards the end. So just a quick chat about what's happening. If I increase the current this way, then we'll increase the flux density. If I increase the current, we increase the flux density. Increase the current, increase the flux density. That's the idea. So if we start, let's do it in a different colour. If we start here at 0, there's no current flowing, we have no magnetism. If we increase the current positively, then we will increase the amount of flux that is in there and the flux density at the poles. So if we increase the current, we increase the flux density. We increase the current a bit more, we'll increase the flux density. And this will carry on for a while, but there comes a point at which no matter how much we increase the current, we can get no more flux density in the space that we have, in the magnet that we have. And our curve will do this, and it would carry on flat. So it's reached what we call magnetic saturation. So we now have a current flowing in here, we have a magnet, and we've got magnetic saturation. So a particular current produces a particular flux density. If I were to turn off that supply, so this now stops, we would think that there is no magnetism, but that's not true, because what happens is when we turn off the current, so the current is 0, that's what is represented by this line here, the current is 0, there is still some remaining flux density in the electromagnet. So our curve will now do something like this. Not the best drawing, but it'll do. So our curve will do something like this. So we have no current, but this has still got magnetism. It has been magnetized by the current. So this little bit of magnetism which remains is called the remnant flux density. So the remnant flux density. So that's that bit there. If we want that flux density to get down to 0, so this is effectively unmagnetized again, we actually have to increase the current in the opposite direction. So in other words, I'm going to put the current in there and out there. So I've changed the polarity of the supply to have to do that. So for that reason, I'm going to call this minus I. So this would be plus I, and that's minus I. Hopefully that makes sense. So as we now increase this current, we'll gradually increase the current, changing the properties of the magnet. We will bring down the flux density to 0. So the flux density comes down to 0, but it took us a current of opposite polarity to do that. If I want to remagnetize this, to make it change the poles, if I want to remagnetize it, then I have to keep increasing this current. And if I increase it, it will do something like this, where we would reach magnetic saturation. No matter how far we increase the current, we'd hit magnetic saturation and it won't get a higher flux density. So once again, if I turn the supply off, so we've got nothing there, if we turn that supply off, there is still going to be some residual magnetism, and that's shown by this area on this characteristic. So we have no current flowing. Here's the current line. That is 0 current there, 0 current. No current flowing, but we have flux density. Again, to get that flux density to 0, we have to go back and put the current in this side yet again. And if we do that, then we get up to there. So I've now applied sufficient current to reduce the flux density to 0. And if we carry on and increase that current, it will take us back up to there. So the red shape here is called a hysteresis loop. Sometimes it's called a BH curve. Talk about that in a second. Just one point here, we've labelled this axis with current that's going positive, in other words it's going in there, current that's going negative, in other words the current's flowing in there. We've changed the polarity. This is the flux density with one polarity, and this is the flux density with the opposite polarity. I did forget to label that earlier. So let's just come back to the current. I've called this I. Technically, it's not called the current. We have B, and this is not I, this is H. And H is the magnetic field strength. So this will be minus H, and this will be plus H. So I just use I to try and develop the diagram, but technically we need to call this H. Once again, that's the magnetic field strength. There is a formula for that, which you don't have to worry about, but magnetic field strength is H equals NI over L. Hopefully you won't see that in any of your exams. So this hysteresis loop is often called a BH curve. A BH curve. So what does it indicate? Well, the area inside this curve indicates it is proportional to the amount of energy lost in magnetizing and demagnetizing the piece of metal.